Hello everyone, in this video we're going to talk about dimension reductions. Dimension reduction is one of the last steps in data pre-processing. It's a step right before applying an algorithms or using the data to find patterns hidden in the data. So this is not most of the time done for visualization or surface level analytics, but once you want to use algorithms to find those patterns, a lot of times you need to do some dimension reductions. In a nutshell, dimension reduction refers to the fact that there are extra columns in your data. The extra columns could be a concern of computational cost, but mainly in this video, and a lot of times when we talk about dimension reduction, what we are talking about is the fact that there are repetition in the columns. The repetition could be as simple as just two columns have the exact same values but under different column names, but it also could be a little bit deeper as far as the attributes having too much correlations to one another. Basically, they are separate attributes or columns, but because they're too similar, they're not really adding anything to our data frame or to our data or to the space of the data that an algorithm wants to come in and find patterns. And the existence of a lot of the same information could be creating bias in your patterns that you're finding, and also it could be confusing the algorithms. So a lot of the things that we will be learning in this module are not going to be applicable to what we've been doing. That's why it comes in the end. It's sort of like step to the next course, which is using algorithmic way of analyzing data and finding patterns. So we're just going to see how it's done in an example and sort of set ourselves up for the next course. So in this video, we're going to be using a new data set and do some dimension reductions and also data redundancy analysis. So let's get to it. Okay, we're going to be using the Boston housing data set that I will be providing for you. And as usual, we import the modules that we have been using and we've been learning about in this course. So this is the data set that we have. So there are some columns here. There are like 14 columns and 506 rows here. And the columns names are not very intuitive. I mean, some of them are, but some of them are not very intuitive. So the their description are provided here, but also they're provided in this file, a PDF file that I will also be providing. So it's good to keep this very close, either like printed or another tab open, because you might have to be referring to this very often when you are doing dimension reduction, because you want to sort of see what these attributes are when you see there are a lot of similarity between the attributes. So this is, we're going to keep this handy in case we're going to need it. And then we also can use a describe function to see some simple statistics to help us figure out more about these attributes. And also we could be doing histograms to do the same thing that these attributes are doing, but it's a little bit more visual than the other one, that can help us sort of start understanding the values of these attributes. So one thing I urge you to do before continuing to watch this video is actually spend some time on your own studying these attributes descriptions, trying to understand what they are, and then look at the mean standard deviation of them, and also look at their histograms to start understanding the data. What are the values? What are the tendency of each attributes? And that's very important once you start working with the data, the first thing you want to do always is get to know it. And that is the steps, these are the steps that you take to get to know it. So stop this video and spend some time getting to know this data. Read the attribute descriptions, look at the statistics, and also the histograms. Once you have done this, now you're ready to do some correlation analysis. Correlation analysis is basically seeing how similar or how much correlation exists between each attributes. So we do correlation analysis for numerical attributes. Or you could be doing correlation analysis for categorical attributes as well if they are presented by numbers, and they give you some idea, but that's not the correct way to go about it. So I've separated the numerical attributes here, and I am creating a data frame only with those numerical attributes. And all you need to do really to get to correlation with pandas is say dot core, which is the function that does correlation, like apply the correlation formula for every possible pair of the attributes. So once we run this, now we have this correlation matrix that we can look at all of the possible correlations. Now that we are using a computer and also we have a lot of like tools here to like do more visualization, let's turn this matrix into a heat map, and it's going to help us spot what we want to look at much easier. And I'm using the Seaborn heat map here, and I'm importing that, and then I'm just using that function of heat map with what needs to go in it, that data, which is that correlation that I calculated, and a couple of other properties that are set that are very simple and intuitive to understand. But it's presented in a way that it's sort of helping my eyes to see high correlations and low correlations. So anything that is too green or too red is basically high correlation. So for example, we have high correlation between indus, high correlation between indus, negative high correlation, and also DIS. So you want to like sort of check what these are. Indus is percentage of land occupied by non-residential business. So this data set, every row is basically a neighborhood. Indus is how much of this neighborhood has non-residential business inside it. And DIS is weighted distance to 5 Boston employment centers. How close this area, this neighborhood is to sort of like, the downtown area like that. They are like, big employment centers. So you can see that there are high negative correlation between them, and that implies that if there is a percentage of land occupied by non-residential business, sort of those areas that there are a lot of industrial businesses or like work being done, sort of like further than where the downtown or like the employment centers are. So that sort of tells you that they are sort of giving you the same information, 70%, but they are they have negative relationship to one another. So to practice this, go ahead and find all of the other ones that their absolute value is higher than 0.7. This is basically the rule of thumb. When during correlation analysis between numerical attributes, when the absolute value of correlation is greater than 0.7, that's sort of like a red flag. You want to like start analyzing and see what's going on, if it's making sense. And once it makes sense, which attributes is more important for you, because a lot of times when there is such high correlation between attributes, you might have to end up removing one of them before going to the next step. Here we are not making those decisions. Here at this level, we're just going to practice sort of like seeing these relationships and like sort of understanding what's happening and if it's making sense or not. So spot all of those values. Do what I did. Just go to the attributes if you don't remember what those attributes were, and sort of see if it makes sense, and which attribute would be more important to keep. You have to pay attention. That's a question that would be much easier to answer once you know why you're doing these analysis. What's the purpose of the analysis? Since we don't have that, that might not be easy question to answer. But sort of like think about it, and if it's okay, it's okay if you don't have an answer, as long as you are like thinking, oh, which attributes presenting what possible valuable information, and what are those. For example, if there is like 70% similarity between them, what are the other 30% that they're showing? How valuable that information could be. So all of those things are good practices that you could be doing with this data set. Another way we could have done the analysis here is, instead of using correlation, sort of use scatter plots of every possible combination of the numerical attributes. And once you do this is basically giving you the same information, but in a more visual way. So you can see if there is a high correlation. For example, here we can see there is a high correlation between LSTAT and MEDV, which is the median value. So there is that high correlation. If you go and check your heat map, you can also see that high correlation here. So it's, it's like any other statistical summary. So you have correlation, gives you a number that very convenient to tell you what's going on between them, but also then you have this scatter plot that it's giving you much more. It's showing you the relationship between these attributes, and depending on if you just need that one number to look at, or you want to like see the relationship closer, you could be using either this or the correlation matrix. Another challenge I have for you is to sort of like look at this visuals of all the scatter plots, find the one that, a couple of them that have high correlation, with your eyes, and then sort of like confirm that with the matrix, the correlation matrix, and sort of like see some of the real value correlation and also the type of relationship that the attributes have with one another. So far what we did, we were able to analyze data redundancy for numerical attributes. How about if we have categorical attributes? How are we supposed to go about finding if there is a data redundancy between them? So for categorical attributes, what we do, we basically come up with contingency tables for the categorical attributes. And contingency tables are basically tables with X and Y, like row and columns, that on the rows, one of the attributes, all of the possible states or levels, and on the other axis, all of the other attributes possibilities are there. And then it sort of counts how many times each cells have representation in the data. And that helps you. So this is like a contingency table for the relationship between categorical, let's see what they are, categorical median value of owner occupied home in the in the US dollar, in 1,000 US dollars, and the categorical median value is basically if that number is greater than 30 or not. So if it's like a richer neighborhood or poorer neighborhood, basically this value shows. And then the other one, CHAS is, does the neighborhood have a border with the Charles River? So if it's close to that Charles River or not, the neighborhood. So you now have that contingency table that sort of like tells you the relationship between these two attributes. You can see that most of your data is at the 0, 0. And then not a lot of your data is at 1, 1. One thing you could be doing is sort of like do a calculation of the percentage. So what is the percentage of the data is in each of those parts? Once you do that, you see that there is not, I mean, there is some relationship between them. There is not that much relationship that one attribute predicts the value of the other attribute. One thing you could be doing, you could also be using a heat map to sort of like use colors to see what's happening there. And again, we can see that being close to the river is not, it is changing the value a little bit. It's making it a little bit more valuable, but it's not a black and white prediction. It's not changing too much. It is changing a little bit, but it's not changing a lot. So there is not that much correlation. And I know at this level, this decision becomes very subjective based on how much change it is, because we don't have a value like correlation, say, okay, 0.7 is the red flag. And that 0.7 being a red flag also shouldn't be taken as a rigid rule that if it's something 0.6 and you don't want to take a look at it. Yes, if your correlation analysis, your data has correlation analysis of no red flags, but there is 1.6 correlation, I would take a look at that. I mean, don't take these rule of thumbs too seriously. And here we don't have a rule of thumb. It's sort of like very subjective, just looking at the contingency table and see if there is that relationship that tells you one of the attributes is redundant. And we can see they are not. It's being close to the river or not is influencing the value of the properties, but not that much. So also, before like looking at these, some of these values, you can see that most of the data is for both cases. Most of the neighborhood is not close to the river, and also most of the neighborhoods are not very rich. So this is another thing you want to pay attention to when you're looking at these values. So you can see 93% are 0, and also 83% are richer neighborhoods. The last thing we will discuss in this video is, okay, so far we have seen we could be using correlation analysis for numerical attributes to analyze if there are data redundancy. And we also see contingency table is great for seeing if there are data redundancy between categorical attributes. But how about seeing if there are data redundancy between numerical attributes and categorical attributes? Well, there are two ways to go about this. One is to sort of give numbers to categorical attributes and sort of use correlation analysis. So you switch the categorical attribute to a numerical attribute. You are making a lot of assumptions there, and then see if there are correlation there. Or the other thing that I like it better because it has less assumption is to sort of strip down the numerical attributes and categorize it. Or what they say, discretize it. Basically means the continuous numerical attributes will have some categories that are representing those values. This also can be known as categorization. So the way you go about the discretization is using the panda function cut. This is something we've seen in some of the videos before. So basically in this code here, I have separated the numerical attributes from the categorical attributes. And for each categorical attribute, I am discretizing the numerical attribute with 5 bins. So this is like a bin number I came up with. It's not that important. It's a number sort of for me to like analyze this relationship. So I'm not going to be using this in the further analysis. The numerical attributes are going to be numerical attributes. But for the purpose of seeing if there are relationships, I'm just using 5, and it's somewhat of an arbitrary number, and that's okay. And once I run this code, now I can see a lot of different contingency tables using heat map to sort of show them. And I can see that most of these do not have a very high relationship. One thing you want to do is sort of study all of these contingency tables and see if you see relationships within them. One of them that does have relationship is this one. It's the categorical value for the median of the value of the properties, and Zn and Zn. Let's see what Zn is. Zn is the percentage of residential land zone for lots over 25,000 square feet. So you can see that there is a relationship between them. If one is one state, as you move towards the other states of the other categorical attribute, you can see there is a relationship. So you could sort of like start sort of being concerned about these two attributes being in your data for some sort of algorithmic analysis. So study all of these. Also look at their descriptions and see if those relationships make sense. A couple of the ones that do have high relationships are listed here. So once you went through all of those by yourself, sort of like check the answer